you. How you doing? I'm Dave Freeman. Bob here. Bob? Good to meet you, sir. I've forgotten your name. West, I'm Dave Freeman. You're over at the chairman of the CVA, who was Dave Freeman. My dad. No, I'm kidding. But my father knew him.
Let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. Ed Tomlinson. Ed is an advisory engineer with the Bettis Atomic Power Laboratory in West Mifflin, Pennsylvania. Ed is one of our own. He is a three-time graduate of this program, receiving BS, MS, and PhD in 1972, 1974, and 1976, respectively. In 1976, he went to work for the Oak Ridge National Laboratory in methods development, and he was there until 1980. And then he left ORNL and went to TVA in Chattanooga, where TVA had, at that time, the headquarters for their engineering work. And he was there from 80 to 82, and he headed up a computational methods development group for TVA in Chattanooga. In 82, he left and he went to Bettis, and he's been at Bettis for the past 22 years. He's not only a respected engineer, the advisory engineer position at Bettis is a very high position, but he's also a good friend. And so we're indeed privileged to have him here today. The topic of his presentation is space nuclear power. Ladies and gentlemen, please welcome Dr. Ed Tomlinson.
Good afternoon. I'm here today, and I'm going to talk to you about some of the new and exciting things that we're doing, especially for the Naval Reactors program. To talk about space reactors is something new. We encourage you to consider employment at Bettis. This is the plug. This is the plug part. We encourage you to consider employment at Bettis, Capel, or BPMI. Capel is the Bettis counterpart in Schenectady. It used to be run by General Electric, now run by Lockheed Martin. We are hiring. Actually, we're trying to hire a lot of people to staff up for this particular work. Requirements are U.S. citizenship and good undergraduate record. We also would like you to consider doing summer interns at Bettis or Capel. They're very competitive, but once you get in, there's very interesting work, and they're challenging 3-month assignments, and you can renew them from year to year. Applications for internships are due early in the school year, as you have to go through an interview at either Bettis or Capel, and you also have to get your security clearance, which takes longer and longer all the time. We also encourage you to consider applying for the Naval Nuclear Propulsion Fellowship. It pays a tuition for graduate study and gives you a monthly stipend. Fellows are required to do summer practicums at one of the labs, working with scientists or engineers in your area of study. I have brochures here on the table, and Lee Dodds has some other information to provide. You can also get information for any of these programs on the web at www.bettis.gov or capel.gov or bpmionline.gov. We also encourage you to do space reactor-related work in some of your design projects that are going on. For nuclear engineering departments, there's an ANS design competition that is in 2005, and Lee Dodds is the man to contact on that, too. Let's see if I can work this. That's the wrong one. What I'd like to talk about today is a little bit about naval reactors and who we are. We're kind of the secretive program that most people don't get to hear about, and we don't get to talk about very often. So I'll give you a little background on what we do, and later I'll talk on how we got involved in this program. Then I'll talk a little bit about the JIMO mission, and it is pronounced JIMO, not JIMO. JPL corrects people all the time when we mispronounce it. And we'll talk a little bit, JPL being Jet Propulsion Laboratory. We'll talk a little bit about the design challenges and some of the issues for space reactors. And we'll talk a little bit also about the space environment and some of the materials concerns. For space reactors, one of the biggies is materials, especially for the temperatures that we're going to be operating at. And I'll also put in another plug for student design work because there's lots of things that could be done. Wrong way. Okay, naval reactors success story. We have, at present, we have over 84 nuclear-powered ships. Okay, and most of them are submarines. The latest class is floating around. There's the smaller, cheaper version is the Virginia class. Well, it was the first one a couple of years ago. The last one that I was involved in was Seawolf, which is a Bettis design. This is a Capel design here. This is the underwater Death Star. Only a few of those were built. And we also do a lot of work at Bettis on Nimitz-class carriers. Los Angeles class has been around a while. NR1, everyone's heard of. Well, where is Naval Reactors facilities located? Well, they're located around, pretty much spread around the country. There's Bettis Laboratory, which is in Pittwater. Now, first of all, Naval Reactors headquarters located in D.C. And there are two laboratories. There's Bettis in Pittsburgh and Capel in Schenectady. And these two laboratories are responsible for most of the design and engineering work. There's also...
Is the D.C., is that NRL?
No, that's not Naval Research Laboratories. It's Naval Reactors. They're part Navy, part DOE. It's 08. If you look at the Naval NAVSEA command stuff, it's 08. It's the group. And DOE, it's under DOE, NE, whatever. So there's part of that, too. So it's a double, from the Rickover days, it's a double-hatted organization. But the two laboratories do most of the design work. Bechtel Plant Machinery has two sites, one in Pittsburgh and one in Schenectady. They are mostly responsible for design of heavy equipment and procurement, pumps, reactor vessels, that kind of thing. In addition to that, there are a number of shipyards that are supported. In each one of these shipyards, there's usually a resident manager, either a Naval Reactors person or a Bettis person or a Capel person and a small staff. There are two new construction yards, one in Electric Boat and one in Newport News. And there's a reactor plant group of 3 or 4 people there that oversees new construction, and they take care of procedures and quality assurance and making sure everything gets there on time. If there are issues that come up, it's their job to handle that kind of stuff. One thing that is missing off of here is there's a site at Yucca Mountain. We have staff there, too. The Naval Reactors program is themed of about 130 million miles. The program currently operates 100 reactors and has accumulated about 5,600 reactor years of operational experience. Through the entire history of the program, there's never been a reactor accident nor any release of reactivity that can adversely affect the public or the environment. And there's a quote from Al Gore, in the right state for Al Gore. It says, maybe not the right state. In the field of nuclear energy, not only has naval nuclear propulsion made a contribution to national security of incalculable value, but it's done so at a level of sustained excellence that is an outstanding example of government serving its citizens. The program's record of safety and environmental protection started long before it was generally recognized how important these things are. It's simply without equal. That was part of the anniversary of the Naval Nuclear Program. I like Al Gore, by the way, but that's worth. Okay, what kind of things do we do? 2 laboratories, Bettis and Capel. The headquarters for the Bettis, the prime contractors, and the prime contractors from the beginning of the program used to be Westinghouse and General Electric. Westinghouse is defunct. We're now run by Bechtel. And Capel was originally run by General Electric, and it is now run by Lockheed Martin. But it is headquarters for the prime contractor operations, and that's where we run everything from there. They are also, this is, like I said before, the centers for all the design and engineering work, particularly in the reactor plant. And we have labs and computers and experimental facilities. We also run 2 training sites, one at Kesselring, which is near the Schenectady site, just outside of Albany, New York, and there used to be one in Idaho, which has been closed down, and there's MTS, which stands for More Training Ships. They are at Charleston Navy Yard. And there are 2 operating prototypes, both at Kesselring, 2 operating More Training Ships, both in Charleston. It's on-hands training that's supplemented by simulators. Simulators is a new thing in the Naval Reactors program. Rickover was not a believer. Newer admirals are, because you can do things on a simulator you can't do on a real plant. And annually we train in excess of 2,100 people. And it's integrated testing, meaning hands-on. You look at the steam plant, the reactor plant, everything. There's also a site in Idaho where we used to have prototypes, Naval Reactors Facility, which is on the INEL reservation, or INEL reservation, or INL reservation, name of the week. There you have an extended core facility where defueled cores are sent for post-irradiation examination to look at things like fuel performance and corrosion and what have you. Get depletion information just so we can qualify codes on how good we calculate depletion. And like it says here, that's mainly what we do there is examination. In total, we have about 5,700 people in the program. This does not include naval personnel. The bulk of our engineers and scientists. We also have technical specialists, technicians, support, and craftspeople. So, soup to nuts operation. Okay, the next thing I want to talk about is the JIMO mission. Okay, this is kind of a high-level overview of what JIMO is supposed to be. The plan is to launch the spacecraft no earlier than 2015. Some people say that's extremely optimistic, and I would agree. It's a very aggressive schedule. The trip to Jupiter will take approximately 6 to 9 years, depending on the time span depends on what velocity is at escape, Earth's escape. If we have to spiral out, it's 9 years. If we can actually launch to escape velocity, it's something shorter. The plan follows after the trip to Jupiter. They're planned for 4 to 6 years of science observations. We'll orbit each one of the 3 moons, these 3 of the 61 moons, Callisto, Ganymede, and finally Europa. They're expected 4 to 6 months. They're going to orbit the science package for a while, changing orbits. And the end of the mission is somewhere in the 2025 range. At the request of NASA, the National Research Council conducted a planetary science community assessment of what the priorities of the U.S. planetary research program should be for the next 10 years. It was called the Decadal Study. The study identified research at Jupiter as being the highest priority, and they had three objectives of this mission. One was the Jupiter Icy Moons Orbiter, and its purpose was to search for evidence of subsurface oceans on these particular 3 moons. It's also out to investigate the makeup of the moons, to learn about the history of the moons if they can, determine potential for sustaining life, not necessarily human life, but is there anything there at all. And also, they pointed out that this mission will require much more energy than you can get from an RTG or solar panels, and we'll talk a little bit more about that in a minute. So the next question comes out is, how did NR get involved in this? What's Naval Reactors doing in space? And we'll get to that here in a second. The last time the U.S. flew a fission reactor in space was nearly 40 years ago, SNAP series. The Russians have done it since then. Matter of fact, there are pieces in Canada to prove it. The JIMO mission need for power and lifetime are far beyond those of any of the previous power programs. We're looking at a 20-year mission here. If you look at the design mission for things like the SP-100 program, we're looking at a 7 or 8 year mission in low Earth orbit or near Earth orbit. JIMO is intended to demonstrate and deliver nuclear electric propulsion for robotic deep space organization, or deep space missions. This is kind of a first. There have been small electric drives used in space before, but this is a major, big-scale production. The launch mass and volume constraints on the spacecraft are usually set by the available launch vehicle. However, right now, we don't have much of a launch vehicle capability in this country. The Saturn V's are gone. It would be a non-issue if that program were still in existence, but it's not. Now we're stuck with Delta rockets, and they have a relatively small payload capability for what we're looking at here, and we'll give some numbers on that in a minute. However, NASA is talking about coming up with a new launch vehicle with higher capability, TBD. Don't count on it, is what they're telling us here. To make this even more interesting, from a nuclear standpoint, is that Jet Propulsion Laboratory has expressed an interest in oversizing the reactors for missions beyond going to Jupiter. They want to go to Pluto. They want to put bases on Mars. And for a while, there was some talk that whatever reactor you came up for interstellar space could also be used on the surface of a planet. There are lots of issues that say that technically that's not possible or not a good way to go or to think about it. The demands for the JIMO mission include 20 years of continuous autonomous operation at an average reactor temperature in excess of 1,000 degrees Celsius. Very, very hot relative to what we're looking at. Major efforts is needed to develop a workable design and validate the performance capabilities of the reactor. So let's put fission power in context of where things stand. If you look at the graph on the left, look at the F-scissor we're talking about. It says duration of use, but think of duration of use as distance. The longer the mission, the further away I'm going to be. Okay. And we're also going to look at electric power level requirements. Okay. How many BTUs per second do I need to get out of this thing? So if you look at the product of these two is energy, right? Time and duration. So increasing energy goes in that direction. So if you're looking at chemical rockets, which you're all familiar with, we're looking at short duration missions. I got to get into orbit, 45 seconds, whatever, for a chemical burden. But I can get a lot of power out of that. Okay? If I'm looking at missions that are going to last months or years or tens of years, I'm moving out in this direction here. Solar panels, they're pretty good. I mean, we can use those. You see them all the time on the International Space Station. The problem with solar panels is that the further you get from the sun, the less the solar flux is, the less useful solar panels are. So if you look at the plot on the right, and you look at distance from the sun in AU is an astronomical unit, which is the distance from the sun to the Earth. And it kind of, so 1 AU puts you right here at Earth. And if you look at the relative solar fluxes, they drop off quickly. So if you're thinking about going to missions on the outer planets here, solar's not going to get you there unless you have the world's largest solar array, which you could never get off the ground. So solar is kind of in this range. Another source of power that's used a lot are RTGs. That's sending plutonium into space, always a political issue. And they're okay for low power levels. They're passive versions, they're dynamic versions where it's hooked to a Stirling engine. But again, you can get the long lives, but you can't get the high power levels. And you can't really use these for electric propulsion. Just don't, there's not enough guts there, not enough oomph to keep things going. So it puts you out here in the fission energy range, ready for the deep space mission where you need electric power to get there. I'll get this right when I'm done. Yeah, excellent. So a little bit of background on JIMO. NASA conducted 3 Jupiter Icy Moon Tour studies between August 2002 and January 2003 to gain insight into mission concepts that would accomplish the Jupiter science objectives. The objectives were the ones we talked about before that were set out by the National Research Council in this decadal study. JPL initiated a feasibility study of a Jupiter Icy Moon orbiter mission in November 2002 and presented the results to the NASA administrator, Sean O'Keefe, who we all heard of, in January 2003. Included in the report was a project plan, an acquisition strategy, and contract RFPs, request for proposals. Congress approved this for the FY03 in the FY03 budget, and work actually started on it in February 2003. At that time, 3 industry teams were set up to go off and do the spacecraft vendor guys to go off and look at some feasibility studies. And the 3 teams were headed, but one was by Boeing, one was by Lockheed Martin, and one was Northrop Grumman. They were supposed to do trade studies and report back on, what's this thing going to look like. And they were supposed to do that by December 2004. That was done early, and just last month, JPL or NASA picked the prime contractor, went to Northrop Grumman, the prime contractor for the spacecraft. A little bit earlier than that, the Secretary of Energy gave DOE NR, that's us, Naval Reactors, responsibility for work on the spacecraft. Sean O'Keefe says that NASA sought a partnership with NR because NR has an enduring commitment to safety and environmental stewardship that is required for an undertaking of this magnitude. Sean O'Keefe quote. This partnership between NASA is consistent with NR's history of supporting fission work for civilian applications, including development of the first pressurized water reactor at Shippingport back in the early 1950s. Specific roles and responsibilities on who's going to do what, essentially, were defined in a memorandum of understanding between NASA and Naval Reactors in August 2004. So this is like hot off the press stuff. I haven't seen it yet. The NR labs are not without relevance in supporting these technologies. Many of you may recall that the second nuclear submarine, Seawolf, after Nautilus, had a sodium-cooled reactor. Lasted a couple years. It was taken out and replaced with a pressurized water reactor. The Naval Reactors Program subsequently published one of the first handbooks on liquid metal technology. The program has investigated advanced reactor concepts, high-temperature materials of direct energy conversion, and has made substantive direct energy conversion technologies available to the public. Since March 2004, the NR program has moved aggressively to assemble combined teams of experienced designers from Bettis and Kaplan. The group has the acronym for the group is NRPCT. It's an acronym without any vowels, which is always hard to remember. But it's the Naval Reactors Prime Contract Team. And if you look at the way it's actually set up, the project office is at Kaplan, and Bettis and Kaplan have what are commonly called integrated product teams working underneath them. Inter-office work orders have been placed with Los Alamos, INEEL, PNNL, and Oak Ridge to support work since they have expertise and experience from previous space-related work. While we were in the learning curve from last March up to now, we have relied heavily on Los Alamos and Oak Ridge to get us up to speed on what's going on in the space world. The DOE Office of Nuclear Energy Science and Technology, which is the old DOE NE50, I believe it was, will retain responsibility for supporting NASA other space technology efforts, things like RTGs, and also long-term research budgets. I must emphasize, though, and I've been told to emphasize this, that our main business is still naval nuclear propulsion, not necessarily space stuff. This may end up being maybe 20% of our business, 20 to 25% when all is said and done. So what is the scope of the NR assigned? What pieces of this whole project are really assigned to the Naval Reactors Program? The overall responsibility for the spacecraft and related nuclear components, ownership of the reactor core, reflectors, INC, vessel, primary heat transport, and shield are our responsibility. We Naval Reactors do that. Oversight, including the requirements for the integration of the energy conversion system, heat rejection system, and electric power systems, are somebody else's responsibility, but we can say, no, you can't do that. And the bottom line for that is the hallmark of the NR program that design development must be done in an integrated sense. We don't have to design the reactor plant without looking at the steam plant on a ship. We wouldn't do anything differently here. Taking a look at what the spacecraft might look like, this is pretty much the conceptual drawing of this changes monthly. So this is the last time we caught a picture. This is what it looked like. There are a number of modules in here. The things we need to look at are, it's broken up into three pieces. We have a controlled fission reactor to produce heat, and we have cooling loops to remove the heat, and we have a power conversion subsystem. If you look at what's going on here, there's, let's start at the front, the valve, maybe. Here's the reactor. The reactor is this little piece here, okay? And there's a shadow shield that's in here, and it's just a shadow shield. It's a cone, okay? So all you're trying to do is protect things that are back here. You don't care what's going on out in front of you to the side. Then there's some kind of power conversion equipment in here. So this is where I turn heat into electricity. And then these are radiators, all this back here. I'll talk a little more about radiators in a second because they're a major driver on weights and size. This piece back here, the mission module, is called bus. And inside the bus is the science package, the xenon tanks that uses xenon as a fuel, its propellant. It also has a lot of the power management and energy electric distribution system. It also is a place to mount all of the telecommunications things. Again, these have to lie inside the cone from the shield. And there's also the electric propulsion pods hang off the back. So the part that Naval Reactors is responsible for is that. And we have right of refusal on a lot of these other things. This part back here is purely NASA JPL directed. They just plug into our electric grid. There are lots of different energy conversion options that are being looked at, and we'll talk about those more in a second. Since all the heat is not converted to electricity, the radiator must be used to radiate heat to space. Okay? Space has a very, very low sink temperature. Around Earth, the sink temperature is about 200 degrees Kelvin. In deep space, it's about 5 degrees Kelvin. Very good heat sink. The problem is it's a very poor heat transfer mechanism to get there. I've got to radiate everything, so I'm looking at T to the 4th. So there's which says it drives me to have very hot radiator temperatures to be able to dump the heat that I want to get rid of. Hot radiator temperatures bring up all kinds of problems, especially when you look at some of the designs. The radiation shield is in here to protect any kind of instrumentation that's going on there, and you also don't want to irradiate any of your science package in the back. Things can't hang outside the cone of the shield because they just act as scattering sources. So then it hits these, scatter back in here. That's a bad thing. And the specific technologies that end up being used will depend a lot on what materials are available. Quick walk through what the power system looks like here. We have a fission reactor up front that just is a fission reactor, standard fission reactor. Neutron balance, you've got shields and reflectors and control rods to control the neutron balance. I have to transport the heat from here, from the reactor, somehow back to the power conversion system. There are a few concepts being looked at. There's a shield to protect things. Here are the heat rejection systems to throw away waste heat. This is not a 100% efficient system thermally. Produce electric power. The electric power goes two places. It goes to the spacecraft bus, which takes care of the vehicle and the payload systems, and the rest of it goes to power processing, electric thrust, and the propellant supply there. The vehicle systems include things like the pumps, primary pumps, secondary pumps. There's another view of that on the bottom. So some of the topic areas that we're looking at in these concepts are reactor coolants. We said there's a lot of different options. There are liquid metals. Depending on the temperature range that I think I'm going to operate in, if I'm looking at 1,300 degrees Kelvin outlet temperatures, water's not going to work there. Even in the supercritical system, you're not going to do that. So we're looking at liquid metals. The prime candidate these days for liquid metals is probably lithium. We've also looked at gas, helium-xenon mixes for gas reactors. We've also looked at heat pipes. Los Alamos has proposed a heat pipe design where I can just use heat pipes to get heat out of the core and then set up a heat exchanger, a heat pipe to gas heat exchanger, and use that. Core material sensitivities. There's lots of issues. This whole space reactor deal is a materials issue. There are lots of core issues. There's lots of spectrum issues. Do I want this to be a fast reactor or a thermal reactor? I probably want it to be a fast reactor because it's small. I don't have room to get moderators in there. And if I did, what form would they be in that I could keep hydrogen in something that's operating at 1,300 degrees K? Materials issue. There are control device options. Do I want to use reflectors, sliding reflectors, control drums, control rods? To be determined. How much do I design for off-nominal conditions, transients like startups, shutdowns, power maneuvers? When we first talked to JPL, their version was, well, you turn it on, and when I get done with the mission to Jupiter, I turn it off. You know, it's never quite that simple. Well, that's a great concept. It's never really quite that simple, and you've got to look at all those off-nominal things. Safety features, launch safety. Unlike the standard safety things you think about in power plants and terrestrial reactors, there are issues here like launch safety, and we'll talk about that a little bit more in a second. Materials and fabrications. What kind of fuel system do I want to use here? I need a high uranium density. So how do I do that? What fuel system do I look at? What kind of core materials do I look at? I've got cladding systems that have to operate at the same temperatures as the fuel. What do I use in there? If I'm using refractory metals, there are all kinds of issues that come along with that. Plant structural materials, same kind of thing, very high temperature. Not only that, these have to be compatible with these. Somewhere I'm going to have to weld them. Or somewhere I'm going to get something leaching out of one and go into the other. Bad things can happen. Sensor materials. I've now got a very high temperature, high fluence field that's operating in a vacuum. It could be either high temperature or low temperature, depending on where my sensor is. What do I build my sensors out of? What are my thermocouples made of? What's my NI look like? I can't change it every 5 years. When I burn out a fission counter, it has to last 20 years. Coolant compatibility. Is the coolant, whatever I'm going to pick for a coolant, compatible with what I'm picking for a fuel here? If I get a leak in a clad somewhere, I don't want the coolant coming in and dissolving my fuel. So there's got to be some compatibility issues there. Shield materials. Oak Ridge has done a lot of work here. What do I do for shields? I can't put lead and concrete up there. That's just not going to work. I'll never get it off the ground. Then there are, of course, aerothermal protection. A lot of this has to do with launch accidents. If this thing's coming back in because of a launch abort, you want to bring it back in one piece so you can go get it. It's a safeguards issue. The Russians thought back when when safeguards was not as large an issue. Bring it in, burn it up, let it disperse, gone. Well, they showed that you can't really depend on that happening. So the philosophy here is bring it back in one piece so I can go get it. Keep it out of, if it falls in downtown Baghdad, I want to be able to get it in one piece. Is kind of a concern. There are more concerns than that, but that's from a safeguard standpoint, that's a big one. You don't want the bad guys getting this stuff. It's highly enriched uranium, so it's weapons grade stuff. Reactor plant, you want to look at pipes, pumps and heat pipes, heat exchangers. These are all liquid metal or gas designs, compact heat exchangers. Shielding issues, arrangements, structural systems, the list goes on and on and on. On the energy conversion side, there are a number of options that are being looked at. There are dynamic options, closed Brayton cycles, Stirling engines, Rankine cycles. You got your thermodynamics book, and they're all there. Things, thought were going to be built. On the static side, there are thermoelectric devices, TPV, thermophotovoltaics, and thermoionic devices. No moving parts. That's very attractive. The downside is all of those devices have terrible efficiencies. Secondary side coolants, I've got to reject heat. I'm rejecting heat at a high temperature. What do I use in those loops? And same kind of issues I have to address here on coolants. Radiator options. What does my radiator look like? And temperature sensitivities for all these. Instrumentation and control. What kind of sensors do I want to use? Radiation-hardened electronics is a major issue. And it's not radiation from the reactor that's the issue. It's mostly radiation from space that's the issue. We'll talk about that more. Automatic control systems. I don't have any operator in the loop. There's nobody sitting there with a scram button and a shim switch to move rods. All has to be automated. And the transit time from a signal from here to Jupiter is hours. So you're not going to be able to do much there. And reactor controllability. Advanced reactors, how do they behave? How do we control them? So lots of things to look at there. So where do things kind of stand for this notion of reactor? Well, right now, according to JPL, the electric requirement is somewhere between 135 and 200 kilowatts electric on the bus coming out of the generators. It started off at 100 6 months ago. It's 135 now. The guess is it'll be closer to 200 when it's finally set. Or maybe 50 when it's finally set. If you look at RTGs, you're looking down in the tens of watts range for power levels that you're getting out of those. Depending on your energy conversion choice, you can translate this back through the efficiency. What's this mean in megawatts thermal in the reactor? Well, if you're doing a thermoelectric guy, you're looking at a 2.5 megawatt reactor. If you're looking at a braking system with a 30% or so efficiency, you're looking at a 0.5 megawatt reactor. Big difference, big range. What my reactors look like when I'm looking at that kind of range? Another thing we need to think of is 20 calendar years. It has to have enough energy to have essentially 12 to 15 effective full power years of energy in it. It's going to operate somewhere between 950 and 1350 degrees Kelvin. The material guys would like it to operate at room temperature. The reactor guys would like to have it, or the energy conversion guys would like to have it operated at 1350. Somewhere in there it's going to operate. So there are also transients. We talked about those a little bit. Startups, shutdowns, up powers and down powers. Shielding. Neutron fluence at the bus, 5 times 10 to the 10th. And they want a total gamma ray dose not to exceed 25 kiloreds. Safety issues, it has to be subcritical when it falls on the beach in Bermuda. And it has to be in one piece so we can go get it. Or if it falls in the ocean, they want to go get it, and they want it to be subcritical. Big issue, it has to fit in the launch fairing. I only have so much space, so much power to get this thing into space. And as with the last week, the same with mass. How much can I get up there? So kind of what's the timeline look like for this whole project? So we're right about here. We took when naval reactors got involved, we were about here. We owe naval reactors a report at the end of this month that says, is there a non-zero design space? It's a feasibility report. Can this thing be built with today's technology or technologies that we think we can develop in the next hour and a half kind of thing? This is very short term. That report's being worked on even as we speak. I'd rather be here than working on that, actually. The 3 months from now, next February, we're going to be talking about down selecting on these concepts. We had 3 or 4 energy conversion options. We have 3 or 4 different reactor options. We have 3 or 4, 5, 6, 10 power level options. Hopefully that will be narrowed down sometime in the February time range. The plan at the moment is to get to 2 concepts, a concept and a backup concept, and then actually go off and do the nuts and bolts design work to get there. At that time, we'll work on the design work. We'll talk about this in a second, and complete the flight unit somewhere in the 2012, 2014 range with a 2015 launch date. Very aggressive schedule. You see in here that we're talking about maybe there should be a prototype. This isn't cast in stone. There may be one. There may not be one. SP100 chose to have one. It never really got built. Their experience with it was that by the time they got it to meet all the rules for land-based reactors, that they weren't going to learn anything from it. Naval reactors have a long history of building prototypes. We've had them in Idaho, we've had them in Kesselring. STC was built before Nautilus and preceded Nautilus, and we also had A1B, which preceded the aircraft carriers on the aircraft reactors on Enterprise. We've gotten a lot of good information from them. Lots of things show up that are unexpected. Gives you a chance to diagnose them, to look at life and aging issues, to come up with fixes before, in our case, before the ship ran into the same problem. And it also points up a lot of materials issues. Problem here is you're not going to leave the plant by a whole lot with a prototype. And there's also the issue of I can't mimic zero gravity, vacuum, 5-degree Kelvin atmosphere on Earth. So do I really learn anything from that? Don't know. That's up in the air, still to be determined. Reactor issues. I'll talk a little more about specific reactor issues in the nuclear engineering department. Mentioned some of these before. Things that are on the plate are what's this reactor going to be? It's going to be liquid metal cooled. It's going to be heat pipe cooled. No heat pipes on it. Or gas cooled. Energy conversion options is Brayton, Stirling, Rankin, thermoelectric, thermionics. Heat rejection system, these big radiators that are sitting out there. They're going to be pumped loose. They're going to have heat pipes. We're going to rely on some kind of two-phase flow in these to help get the heat out there. What temperature are they going to be? Intermediate temperature or high temperature? The low efficiency guys, low efficiency energy conversion options have very high temperature radiators. The others are higher efficiency. They're lower temperature radiators, but they're much bigger because they're bigger because they're at lower temperature. They're smaller because they're rejecting less heat. You got to play the trade game. Also, things that are being trying to figure out, or it's going to be an AC or DC electric system, makes a difference, and it could determine which of these you're going to look at. Also, is it going to be a high voltage, low voltage system? Don't know. The interesting part is you can take this whole spacecraft and you're going to fold it up to try and fit in this fairing. You can see here's the bus, here's the boom. For practical lengths, that boom is about 30 meters or so when it's extended. The power conversion units, reactor shield, the reactor sitting down here in some kind of nice cage. This shakes a lot when you launch it. So you've got a design for shock loads, but only for about 45 seconds. So that's kind of some of those issues. There are also some other challenges. We talked a little bit about launch limitations on size and weight. It's a fairing issue. It's a launch vehicle capability issue. Like I said, if the Saturns were in existence today, that wouldn't even be on the chart. Nuclear electric thrust limitations. If you look at thermal thrust from an ionic engine is low, but you can do it for a long time because it's a very efficient system. The thrust you get from an ion engine is about as much, the force you get out of an ion engine is about the same as the force of a sheet of paper laying on your hand. It's not very much, but apply that over 10 years, you get a lot of acceleration out of that, F equals ma. Again, heat sink issues, we talked about that, good temperature, bad mechanism. Zero and reduced gravity, you can't depend on natural circulation. You turn the pumps off, the flow stops. There's nothing to drive it. No thermal head. Vacuum is an issue for lots of areas, some that you wouldn't expect. Electronics cooling. When you got a box of electronics sitting somewhere in a control system, you usually depend on air convection to cool it. Can't do that here, so it's all got to be actively cooled. Lubricants are an issue. In vacuum, lubricants tend to off-gas things. If you have a lubricant that off-gases oxygen, and you get oxygen into a liquid metal system, you get oxides forming, or if you have refractories floating around, oxygen and refractory metals at high temperatures are a very bad combination. Launch loads we talked about. Automatic operations, there are two big ones here. JPL says there are going to be 45 days when you're behind a planet and you can't even talk to this thing. Matter of fact, they don't even monitor this thing continuously. They'll check in every week or two to see if it's still there because they can't afford to run the tracking systems all the time. Also, you're looking at 60 to 100-minute round-trip communication. We're looking at a very cold environment. Get rid of that. Yeah. Looking at very cold environment. So I've got an environment that's very cold. I've got a reactor that's very hot. Got all kinds of stresses, mechanical stresses set up because of that. Everything starts off at Earth ambient temperature, and then they go in either direction. It's a structural issue. Micrometeoroids are an issue. This thing's being shot at with all kinds of micrometeorites at the time, all the time. So you've got to armor people. Radiation environment is an issue. If we have time, we'll talk about that. And you have no chance for maintenance. There are other challenges: fuel system, the cladding. It's a fast reactor. We don't have tons of experience with fast reactors. Control systems we talked about. Actuators. There's mechanisms, rod drive mechanisms or slider mechanisms. We're looking at very fine tuning. We're looking at a reactor that's on, stays on, runs all the time. So the only thing you have to compensate for is depletion. So I'm looking at 6 or 7% burn up. So I don't have to move my rods very much. Well, actually you do, because you're in a vacuum environment. I've got to worry about vacuum welding. So occasionally I'm going to have to tweak these things just to make sure they still work. So you have to think about that. Coolants are an issue. Talked about a lot of these. There are new components that we haven't talked about before. Electromagnetic pumps, HELIX. Not a lot of people building those these days. Who's going to build them? What kind of quality assurance do you need? How are these going to operate in space? I've got to be able to cool because I have a 1,300-degree cooling going through them, or 11 if I'm in the cold lane. So there are issues there on where's the infrastructure? A lot of this is infrastructure issues. Gas separators. If I've got a helium coolant, I radiate helium. I radiate lithium. I get helium in the coolant. I've got to get that out of there because I have gas flowing through an EM pump. It's not going to work. So there are issues there. Things that need to be designed. NH conversion, ground testing, launch safety. The environment, here we're talking about solar flares, geomagnetic meteor storms, and magnetic substorms. Hopefully we'll have time to get to that. So some of the key issues, radiation and micrometeoroid environment, they consume time and cost because I have to design in redundancy if I want to just put them out there and have 10 of them so I can get by on the mission if 2 fail. Or I can armor these things, which costs me in weight. Weight and cost, either way, you're going to lose on that one. So you've got to be imaginative on how you do that. Mass constraints by the nuclear propulsion system. The propulsion system gives you so much F, it's F equals ma. If I go up in mass, I go down in acceleration, the trip takes longer. The dimensions of the payload and the fairing are an issue. We talked about that a little bit. And design analysis and the ability to protect the public. Safety is a big issue on this. There's been lots of issues in the past about launching RTGs, and there were always protesters out. First time we went to JPL back in March to get our Space Reactors 101 class. The day we left, they had their first protester for this project out in front gate. So it starts early. And the bottom line is that NASA and naval reactors and DOE have to do a good job of selling the safety. That's always been true for nuclear power. One of the things the materials guys want to do is reduce the outlet temperature, just because colder is better from a materials guy's standpoint. What's going to cost you? Well, if I do that, here are the two leading concepts, or two concepts, is the thermoelectric static converter issue and breaking cycle issue. This is kind of the radiator surface temperatures we're looking at. For these guys are around 500 degrees Kelvin. For those, about 800 degrees Kelvin. If I reduce reactor temperature, I reduce efficiency. Everything goes up. Boom, the size of my radiator, the area goes up. So I have to play the trade game here. I may not be able to get this in the launch fairway. There's trade-off studies that need to be done. Kind of an idea what's going on. This is what, like the reactor module. This is for the heat pipe reactor. Here's a reactor, 3 heat exchangers, heat pipes run down here, back to the secondary side, Brayton engines, closed cycle Brayton engines, and radiators. The issues are pretty obvious. Long terms at high temperatures for materials, high neutron fluences, can affect material properties. We don't know that. Wear and bearing on moving parts, effective vacuum and high temperatures. Uncertain mission demands. Once it's out there, we don't know what it's going to be doing for 20 years. may want to shut it down, turn it around, slow it down, run at some lower power level. Don't know what that looks like yet. That affects your control system a lot. Assuring sufficient shutdown reactivity for subcriticality on launch accidents. When this thing does dump into the ocean, I don't want it to be super critical, but I got to put enough excess reactivity in it that it's going to last for 20 years. Okay, and I also need to come up with resilient instrumentation. Here are the launch accident issues. We worry about things like propellant fires on the launch pad, propellant explosions on the launch pad. The main thing here is to protect the public and the environment from radioactivity and chemically toxic elements. There's lots of them in there. Beryllium reflectors are a chemically toxic substance. You also have to worry about landing in the ocean or in the water, or in the ocean or on land somewhere. There are compaction accidents. Don't want to compact this thing. It might, want a criticality due to that. You have to worry about spectral shift. If I dump this into the water, I've got an out-fast reactor that's looking at moderation. That's usually a bad thing from a reactivity standpoint. And I would also have to look at things like wet sand. It may be a better reflector than water. Oh, and fuel relocation if it does come apart. Space environment. The big topic here is, where's all the radiation come from? Well, there are solar flares and solar winds, and there are heavy protons and coming from the sun. There's interplanetary cosmic rays. Lots of things get trapped either in the Earth or in Jupiter's orbit that you have to live through. If I can get some numbers here. A lot of this is based on what scientists think. There's some data on some of this stuff. It's estimated that about 75% of the radiation that impacts the spacecraft will come from the environment, only 25% from the reactor. Just take a look at this picture. On the sun side, this trapped particle field comes out about 10 Earth radii and about 200 on the other side. It's even bigger on Jupiter, where the cosmic rays get trapped. Okay, what kind of radiation makes up most of these fields? Well, where's it coming from? If you look at the space environment, the Earth's radiation belts are the near Earth sources. Solar flares, when you get out away from the Earth on the trip to Jupiter, you get into the Jupiter radiation belts when you get there. And you also have deep space background, which is beating on you all the time. That's always there. And there's also an onboard power generation source, so you do get some radiation from the reactor. I'll show you what kinds of radiation here in a second. When you're in the Earth's radiation belt, if you go through the scenario where there's not enough launch power to actually launch this thing to escape, and you've got to spiral out, turn on the engines, run around the Earth for 2 years until you get enough escape velocity to head off to Jupiter, you're going to be hit with protons and electrons. We're talking 100 MeV protons. Trucking along, they're not little guys. Solar flares will give you protons and heavy ions. Jupiter's radiation belts, you get all these and heavy ions. These ions go up as heavy as iron. So that's a bullet coming at you. And there's always deep space radiation, which is usually heavy ions. There is some data that was taken from spacecraft that have been out on their way to Saturn or outer planets. The Ulysses spacecraft in 1992, Pioneer 10 and 11 in 73 and 74, and the Voyager spacecraft in 79. Is one piece of information here. The Jovian radiation atmosphere gave the Galileo spacecraft more than 4 times the radiation it was designed to withstand. The intensity caused failures in the computer circuitry on Galileo. This caused the computer to switch off and go to back up and shut down. Once Galileo cleared the Jupiter radiation fields, it came back to life again. So they healed. There is some good stuff there. There was some annealing going on. Materials issues. In the world of materials, thermodynamic rule. You have to have this thing chemically and thermally stable, your fuel system, because you're going to be changing the temperature here. For the fuel system, you need dimensional stability and chemical stability. We talked about this a little bit before. You don't want to be dissolving the fuel pellet if you get a leak from the clad. We also need tough, ductile, fabrical materials. Some of these concepts have very complex geometries. I want something that I can actually make it with, not something that's going to break or crack or stuff stresses. And I also need radiation-tolerant electronics. On the energy conversion side, there are some low-efficiency devices. Okay, on the static side, you got low efficiency that gives you a high radiator. There's thermal expansion mismatches. If you look at thermoelectric devices, they're made up of stacks of different kinds of material, and they don't all have the same coefficient of linear expansion, so they grow out of phase, and they tend to set up cracks. There's also insulator breakdown, dielectric breakdown under radiation. You get something like this. This is kind of neat. A piece of lucite that's been irradiated, and the dielectric breaks down. One of the guys at JPL calls this freeze-dried lightning. This is kind of what it looks like. It's in a piece about that big, like inch by an inch. On the dynamic side, there are questions of working fluid retention. How do I keep helium xenon in a Brayton engine without leaking out into space for 20 years? There's no inventory makeup system. There are bearing life issues. There are joints of dissimilar metals. How do I weld those without getting intermetallics between them, which are bad for welds? Mass transport issues. If I've got insulators that off-gas oxygen and they get caught in the coolant system and it moves down to the reactor system that's made out of refractory metals, I'm in trouble. There's a material issue there. And also stability of all the working parts. This is kind of neat. This is a 2-kilowatt Brayton that's run in a vacuum chamber up at NASA Glenn. Fuel issues. The major fuels that we're looking at are uranium nitride. It's very high uranium density, which is good for a fast reactor. Has high thermal conductivity, which is always a good thing. But it's got a low chemical stability. Not a good thing. We've looked at UO2. Actually, and the database here is rather small. It bridges as most of the database, and it's pretty small. UO2, we know a lot about UO2. Low density, low uranium density, low thermal conductivity, not good things, but it's very stable. Now, the fuel system we're looking at is UO2 moly cermets. Cermet's kind of a ceramic with the fuel in there. They resist growth and swelling, have high conductivity, but you can't get the uranium density up very high. And again, big issue here is not a large database on any of those. Okay, 2 seconds on let's talk about student design work. You want to go close? Okay, student design work. Lots of things we're looking at. Operation in the Earth's biosphere. We're looking at the differences between space applications and terrestrial applications. Here, obviously, a no for space. It's an issue for terrestrial stuff, reentry and launch accidents, risk, remote setup, lots of different areas where student design projects could be done. And so you need to consider looking at some of those. And here are some potential design projects. Look at some of the energy conversion systems and radiator trade-offs, alternate shielding materials, alternate fuel enrichment. We're looking at 93% uranium here. You can't use plutonium. It's an international treaty. You can't use plutonium. Reactor dynamics. How do these systems work dynamically? Assuring safety issues, subcriticality. Control mechanisms. Is there something besides control rods, sliders, and drums? Is there another way to do that? Any kind of new reactor concepts. Reduced fuel temperature is always a good thing, and there's lots of bright people in school these days. I'm sure there are other things there. So after that quick rush through, again, are there any questions?
We have time for questions and comments.
Yes, sir.
Well, there was a SNAP program in the late 60s and early 70s.
Yes.
That failed when the specific mass went above about 8 kilograms per kilowatt. I was waiting to hear what the target was for this program. What would it be?
We're looking at The total, I don't know what the alpha is for this mission, what the target is. Depends on the spacecraft and where they go. There are scenarios where there are multiple launches, so we can do this in pieces. So that all floats around a lot. The numbers I've seen floated around are, for the whole spacecraft, numbers on the order of 23,000 kilograms. There's a 14,000 kilogram xenon fuel tank that gets loaded later. They're talking about launching this thing in pieces, loading the xenon in, then loading up boosters to really shoot it off. Part of the mass issue is, given a rocket capability, a launch vehicle capability, can I go to low Earth orbit or high Earth orbit or escape? There are those variables floating in there too. The number that's floating around on specific mass is all over the map. There's nothing else
That's
yet.
applied to the propulsion system, basically.
Right. Yeah. The numbers I've seen from the Los Alamos studies have been around 6,000 kilograms for the reactor and the shield. I don't know where the SNAP stuff was, or SP-100 for that matter.
We have 3 questions from cyberspace.
That's fine.
First question comes from Leonard Palco from ABS Consulting, and he wants to know, how is the program planning on responding to the public concern about launching a reactor into orbit?
That's a very good question. As you know, and I talked to you a little bit about the issues that came up and the protests that came up for the, I guess it was Galileo, when there was an RTG, plutonium-fueled RTG launched into space. There were lots of protests on that. A lot of these issues would be handled through the NASA side, the way they handle that. The best thing we can do is have lots of education programs going on so people understand that the technology really is safe. There are issues. We're going to try and address the issues and be upfront and be open with them.
Okay, good answer. Bill, do you have a question?
Who is working on the instrumentation controls for these reactors?
Jet Propulsion Laboratory has done a lot of work on radiation-hardened computers. Their estimation for I've got some numbers. Their estimate that the total dose they expect to see on the instruments is something on the order of 8 megarads. But they're claiming right now the best computer memory they've seen is good for about 7 kilorads. So there's a lot of work needs to be done there. A lot of shielding needs to go on. But JPL has done a lot of work on that. And I know Oak Ridge has done some work on instrumentation and controls too. Give you an idea on doses, because that directly addresses what you're talking about here. For the international, this is from JPL, the International Space Station, they expect to see doses. This is behind 100 mils of aluminum, okay, 100 mil aluminum shield. They expect to see doses on the order of 0.38 kilorads per year, okay? For a geosynchronous satellite, okay, which is right up in the radiation belts, they get about 50 kilorads per year, okay? For the Europa orbiter, okay, which is just going to go out and orbit Europa, not do anything else, they're expecting a lifetime dose of 3,260 kilorads. For this spacecraft, for the total mission, they're expecting an integrated dose of about 6,000 kilorads, 6 megarads. So it's a challenge. The radiation environment is a real challenge here. And it's not necessarily neutron shielding we're worried about here. This is charged particle shielding.
Let's go to the next question from cyberspace. The first, there's a comment here. The comment and the question comes from Turkey, from Benin Baslo in Turkey. He wants to he says, I would like to thank Dr. Ed Tomlinson for delivering a very nice presentation.
Well, thank you.
My question is, would the GEMO design be subject to NRC licensing, and would it benefit from a legislative exemption as in the past NASA missions involving RTGs?
The licensing issue is, again, one of these up-in-the-air issues. The last I heard is it would be licensed the same way that other NASA work has been done, which goes through a presidential review board, and the president signs off and says, launch this thing. There is a review panel that oversees the safety and design aspects of that, and the NRC has membership on that.
And then one final question from cyberspace. This question comes from Vernon Guthrie, Have you considered a multiple small reactor, modular reactor design to help ensure functional reliability and diverse power options?
That will give you functional reliability and diverse power options. The problem is getting it up there, because if you have multiple units, even if they're smaller, the mass is usually prohibitive to do that. There is something about economy of scale. So if you make them bigger, they usually are more lower alpha.
In the interest of time, I'm going to suggest we do have more questions from the local audience, that those questioners come downstairs and join us at the reception, and Dr. Tomlinson will be down there to answer more questions. But before we adjourn, we do have the reception downstairs, and everyone is invited. But let's express our appreciation again to Dr. Tomlinson.
Thank you. And answer some more. I can answer some. Collect all this stuff.
Yeah.
If anybody's interested in brochures, they're here. You want to keep those?
Hey,
Yeah.
Dave Freeman.
Hi.
I'm from Oak